nice. Hey guys, in this video we are going to learn about continuous charge distributions. Now, what is a continuous charge distribution, you might ask? Well, it's anything that looks like this, or maybe is a curved piece of wire, or maybe even is potentially a disc. Whatever. It's any kind of a shape which you can say is definitely not just a simple point charge. Okay? Now, we won't actually, in AP Physics, need to do long straight wires. So I'm just kind of using this as a sort of introductory example. Just sort of a, hey, did you know? Fun fact. If you do integral calculus to find the electric field, which is actually how you have to find the electric field for something like a long straight wire, you get this horrific expression, which definitely is not equivalent to kq over r squared. Now, what kind of continuous charge distributions will we actually need to do in AP Physics? We will need to do not long straight rods ever. It'll be curved bits of wire that look like the letter C. Actually, they don't all necessarily have to look like the letter C. They could look like, more of a letter C or less of a letter C, right? Whatever, it's some curved, circularly curved distribution of charged, say, wire or whatever it may be. And they will always ask for the electric field for this kind of thing at what's called the focus or the center of curvature. All right, the other kind that you'll have to know how to do is a ring of charge. And for these ones, you'll always be asked to find the electric field somewhere along the central axis of that ring. So I'm kind of drawing this ring from the side, which is why it looks like an oval, right? Use your imagination, right? It's a circular ring of charged wire, and you're supposed to find the electric field here, which is somewhere along the central axis of that thing. Those are the only two continuous charge distributions in AP Physics that you'll have to find electric fields and electric potential for using integral calculus. All right, there are other types of charge distributions where you can use, say, Gauss's law. So, for example, if it's a solid cylinder and you want to find the electric field somewhere reasonably close, you use Gauss's law for that. If you wanted to find the electric field for a plane, again, that's a Gauss's law problem. But these shapes aren't sufficiently symmetrical that you're even allowed to use Gauss's law for them. Gauss's law is based on several different assumptions, the most important one being that you have a highly symmetrical charge distribution. This is definitely not, it's symmetrical along this axis, but that's it. You've got 1 degree of symmetry, so to speak. And so that's not enough for Gauss's law to be useful. Okay, so your alternative then is integral calculus. So what's that going to look like? So here are the steps then for continuous charge distribution problems. And you should be able to find these steps in the notes packet, which you were provided for this class. But here goes. The first thing, choose an equation. That relates to the fact that maybe sometimes you're asked to find the electric field due to an object, and other times you're asked to find the electric potential. So depending on which one you're being asked to do, you'll pick one equation or the other. If they ask you to find the electric field, it's going to be this one. Which is essentially just kq over r squared, but it's got this dq thing in there, which we'll talk about what that is in a moment. And also r hat, because it's a vector function. And then also the formula for electric potential, which is that. So depending on which thing you're asked to do, you will choose one of those two equations. All right, next thing is choose an origin on the object. If it were a linear charge distribution like we used sort of in the intro, These ones are a little bit harder to pick an origin for because it depends where exactly you want to find the electric field. Most of the time, though, what we'll be doing is using a curve, right? And so for something like this, if you want to find, the field, say, there, you would pick an origin right there in the middle of the object. You need to pick an origin in order to make defining the variables for the problem easier. Meaning, what is dq? What is r? What is r hat, right? All of those things depend on choosing an origin and then doing the next step, defining the variables using the diagram and a charge element. All right. The idea of doing integral calculus here is this. If I have, again, I'll go back to the linear charge distribution. I can't really pretend that this thing is a point charge. I can't say all the charge is right here, right in the center, right? That's not quite correct. On the other hand, if I wanted to find the electric field for it in kind of a sloppy way, not the right way, I could get a little better if I, say, divided it in half. And then I said, I've got 2 point charges located there and there, right? This would do a little better than pretending I had 1 single point charge right here, but it would still be not quite correct, okay? So it would be, a vector sum, right, of those 2 things. And again, I could do better if I kept on subdividing it. If I chop it up now into 4 pieces, and I add up those 4 individual vectors, you can probably see where this is going. We need to get the right answer, take our object and divide it up into an infinite number of infinitely tiny charges called charge elements. And then we have to somehow add all of those up as a vector sum. That's calculus. That's what that is. All right, now, we're not doing lines, but the idea here is the same, right? If I've got a curved bit of charge here, I have to draw a random charge element somewhere on there. I'm just picking my favorite little tiny bit of charge. How about this one? I like that one. Don't pick one on the end, and don't pick one at the origin. It needs to be at some just random point along the object. And that right there is going to be our particular favorite charge element of reference. Okay. Next step is in our equation, we're going to put dq in terms of, it says L, R, or theta. All right, now in your notes packet, there is a substitution that we'll be making for dq, and that is that dq equals lambda r d theta. All right, now where that's coming from is kind of a throwback to some of the Gauss's law stuff that we did last year. If you recall, lambda is charge divided by length, right? It's called linear charge density. Okay, so it's Q over L. Okay, now if I rearrange this to solve for Q, it would say Q equals lambda L. If I take the derivative of both sides to turn it into like a differential equation, it would say dq equals lambda dl. So the idea here is that there's a teeny tiny bit of charge on a teeny tiny bit of length along my object. And if it were a straight object, then this is what we would use. We would just say dq in our equation up here, or in this equation, equals lambda dl. And that's all we would have to do. All right, if it's a curved bit, though, then we need to go back to an equation from geometry, which is the equation for arc length. Okay, so another column here. The length of an arc is, for a circular arc anyway, r theta. In other words, it's the radius of it times the number of degrees of a circle that it goes through. Okay, fine, not degrees, radians, but whatever. Okay, it's, r times theta is the length of a particular segment of some circular curve. Okay, again, I can take the derivative here of both sides, and we end up with that. Make a substitution now, and we get that dq equals lambda r d theta. Okay, and so in all of the problems that we are going to do this semester with continuous charge distributions, we'll replace dq with lambda r d theta. So you don't necessarily need to go through this process every single time. You just need to know, for our class, for the purposes of the AP, every time this is what I'll put in for dq. Later on in college, you might do something else where say it's a linear charge distribution, or, oh no, it's a parabolic curve or something else. And obviously in those situations it gets a little bit different, right? Because this only applies to circular curves. Okay, but be that as it may, this is what you'll use every time for this class. Okay, so we've done step 4, and then finally step 5, determining the limits of integration. That's going to be based on how much of a curve you've got. So if it's a curve like this, then it's based on the number of radians from here to there, where, remember, 0 is in the middle. So that's going to mean that, half of your charge distribution is up here, half of it's down there. Therefore, if this were, say, like pi over 2 radians in all, then it would be from pi over 4 to negative pi over 4 for your limits of integration. Okay, now, I know I've done all of this without referring to any specific example, and that's okay. That's kind of what I was going for in this video, trying to be as generic as possible just to introduce the idea of continuous charge distributions. The next videos, I'm going to do a curve, and the video thereafter, I'm going to do one of the ones where it's a complete circle of charge, and you're trying to find the field or potential somewhere off of its axis. Okay, so stay tuned for those next videos.